My name is Jonah Siekmann. I am an undergraduate research assistant at the Dynamic Robotics Lab at Oregon State University. Today, I'll be sharing with you some of my lab's recent work in applying deep reinforcement learning to bipedal robotics on the Cassie robot using recurrent neural networks. Our previous work in applying deep RL to legged locomotion thus far has used simple feed-forward neural networks with a great deal of success. These controllers were a significant contribution, but tended to be somewhat unstable at certain tasks. We've iterated upon this result and have been able to fix some of these deficiencies using a type of recurrent neural network called a long short-term memory, or LSTM, motivated by a desire for the neural network architecture to be able to learn to remember pertinent information about the world which can only be inferred from multiple observations across time. We feed the LSTMs the robot's estimated state, which includes things like pelvis orientation and joint positions and a desired forward speed. The LSTM produces desired motor positions, which the robot's onboard PD controller turns into motor torques. Here, we see that LSTM networks outperform feed-forward networks in simulation by a wide margin, which is encouraging. However, when evaluating both types of network on hardware, we see that the LSTMs actually perform slightly worse than feed-forward networks in their ability to remain upright while controlling the physical robot in the real world. So it seems that the computational capacity of the LSTM is actually working against us. It is overfitting to the dynamics of the simulation and learning behaviors that abuse simulation physics to the detriment of real-world performance. Consistent with the experiences of others in recent years, we find that a powerful solution called dynamics randomization addresses this problem. Dynamics randomization is the practice of randomizing certain important parameters of the dynamics during training. These parameters include, for instance, joint mass, joint damping, inertial parameters, and center of mass of the pelvis. The effect that dynamics randomization has on the success of a sim-to-real transfer is pretty huge. Training with dynamics randomization creates walking controllers which are very robust and can walk for at least 40 seconds on the treadmill, and most of them indefinitely. Here are two side-by-side videos of LSTM networks. On the left, we have 9 unique LSTM networks, each initialized with a different random seed, and on the right, we have 9 LSTM networks initialized with those same seeds, but trained with dynamics randomization. As you can see, the ones not trained with randomization successively fall over in all but 2 cases, whereas the LSTM networks trained with dynamics randomization do not fall. Since the LSTMs could learn to use their memory to record disturbances and make inferences about the environment, we conducted an experiment to see if it was encoding these randomized parameters into its memory. To do this, we trained decoder networks to predict parameters of the dynamics like pelvis center of mass or joint damping values when provided with a snapshot of the memory of the policy network. We used supervised learning with the training set of 40,000 memory states and the corresponding 40,000 dynamics parameter labels which the networks try to predict, and evaluate the performance on a test set of 10,000 such pairs. In this video, you can see one such decoder network attempting to predict the current pelvis center of mass as it is randomized over and over again, using only the memory state of the policy. Using a technique called principal component analysis, we can also visualize the memory of the recurrent policies as they change over time. This video plots the state of the memory as 2-dimensional points, and if we visualize this projection over time, we see that an interesting shape emerges. The resulting projections are consistently periodic and often resemble an ellipse. One interesting, and perhaps obvious thing that we could infer from this is that the LSTM learns highly cyclic behaviors, which is something we would want in a bipedal walking controller. Some key takeaways I hope to leave you with are that RNNs and LSTMs, when trained with dynamics randomization, appear to be very helpful in overcoming the sim-to-real problem. In addition, the memory seems to be doing reasonable things, like memorizing parameters of the environment which are subject to change. Thanks to my fellow lab members, and thank you for your interest and time. If you're curious about any details, I encourage you to read our paper. If you have any questions, please don't hesitate to reach out to me.